Hi, all. My name is Vince Bridgers, and I'm talking to you from Austin, Texas. So today I'll be presenting how to use the Clang static analyzer. So I'm going to present a soup to nuts view of how to use a static analyzer, from a small amount of theory to a practical example. And I'll show you some real open source projects using the static analyzer and the results that we get from using that tool. So we'll talk about why static analysis, why it's interesting, why it's important. We'll talk about static analysis place and continuous integration. We'll also talk about what is cross-translation unit analysis and also how Z3 can help with static analysis results. And as I said, we're going to use the static analyzer on an open source project in a demonstration, and so you can see how it's used. So why tools like the static analyzer? Well, the simple answer is because of the cost of bugs. If you look at this particular graph from a paper by Kaspers-Jones in 1996, you can see that most bugs are introduced early in the development process and are coding and design problems. But most bugs are found during unit testing where the cost is higher to fix those bugs during that phase of development. And as products are released into customer environments, the cost of fixing these bugs grow exponentially after the release. So the cost of bugs is very high. So the conclusion is the earlier that bugs are found, the more bugs found earlier in development process translates to less cost. Now, there are other uses for static analysis tools, such as code acceptance from third parties that you buy code from. As part of the code acceptance process. We're not going to cover that, but you can use your imagination and use these tools to help you increase the overall quality of your code that's developed internally and also delivered from external sources. So how do you find flaws in source code? Well, the first stage is at the development level. You use the compiler. The compiler will tell you about some bugs and they will warn you about others. But they can't find all issues. So one thing that most people do is they run their code through internal code reviews. And that can be useful, but it's also very subjective. And you end up getting sometimes into a lot of discussions. So how do you automate this process and take out the subjectivity and try to make this review process more objective? Well, one way to do this is using automatic tools. We'll discuss that. So there's also linting checks like Clang tidy. There's lint tools like this. So static analysis works by using symbolic execution. The analysis is performed executing code symbolically through simulation, exploring the program for bugs. Another way to find bugs is through dynamic analysis. So examples of this include undefined behavior sanitizers, thread sanitizers, address sanitizers, and those work very well. Those work by instrumenting and running the code on a real target. One of the downsides of these tools is it's difficult to run the entire program and cover all the paths. It's very dependent upon the test cases. So static analysis can help with some of those sorts of things. So I'd like to cover what I call the 4 pillars of program analysis. And we'll run across the rows so that I'll show some examples, whether these are expected to have false positives or not, a few notes about the inner workings, and the compile and runtime effects. So compiler diagnostics are the first line of defense. Pretty much all compilers have this, Clang, GCC, CL. You don't expect to see false positives with diagnostics, but it can happen, but it's usually considered to be a bug. The inner workings are usually just programmatic checks based on the compiler developer's interpretation of the language specification. There's really no compile and runtime effects except for the CPU time it takes to run these checks. The next phase are linters and style checkers. Examples include lint, Clang tidy, Clang format, and sparse for Linux. You may see some false positives for this, so sometimes these need to be filtered by people. The inner workings include looking at text and doing some sort of abstract syntax tree matching. And there can be an extra compile step. The next pillar is what we're going to be focusing on today, specifically with Clang, is static analysis. So examples include CPP check, GCC 10 plus, GCC 10 plus, and Clang. There can be false positives. Sometimes results do need to be reviewed by a human to make sure that they are what's expected. The inner workings use symbolic execution. Usually there's an extra compile step or extra processing that's involved. And the last pillar is dynamic analysis. Some examples include Valgrind, GCC, and Clang include the sanitizers for this purpose. False positives are not likely, but they're possible. Inner workings include injection of runtime checks and a library. And there's usually an extra compile step and extended runtimes. So none of these are really any better or worse than the others. So it's very difficult to compare these. So that's why I refer to these as the 4 pillars of program analysis. You need to use the appropriate tool for the appropriate sort of bug that you're looking for. So all of these tools are available to you to help you find bugs in your source code projects. So with that, we're going to focus on static analysis. So let's talk about a typical continuous integration loop with automated analysis. So the first step would be a programmer makes a code change. He submits it to a continuous integration system. And there's an automated program analysis step that will perform analysis on the code before it's actually submitted to the overall, your internal review system. And this will report coding errors back to the developer. This can be done at the developer's desk. It can be done through machinery. So the next step may be a manual code review, and usually this is subjective. So it's usually based on somebody's opinion, or it can be. You may have internal coding standards. But the really nice thing about automated program analysis compared to a manual code review is that automated program analysis can occur almost instantaneously or as fast as a machine can run the analysis compared to submitting code to a review system and then having people review the code and get comments back to you. This is particularly interesting in organizations that are geographically distributed and also where you might want to push some of the more subjective portions of your review and your coding standard to machinery so that to remove that subjective part of the code review process. And then finally, there's some sort of unit test or end-to-end testing that occurs. And when all of this passes, your code is ready to commit. So you can do syntax, semantic, and analysis checks. You can analyze properties of the code that cannot be tested, for example, coding style. Automated program analysis can automate and offload portions of the manual code review, removing that subjectivity, making it more objective and based on machinery. And it also tightens up the CI loop for many issues and allows you to push, be more productive overall. So if you don't have something like a CI loop with automated analysis, you should probably look at this. Many modern organizations have this. And Clang static analysis can be a key component of this process. So how would you find bugs with the compiler? So here's an example. So this has a simple format specifier issue. If I run the compiler on this, it warns that there's invalid specifier and there's format extra args. This is something that the programmer should look at. So this is before the static analysis step. So while compiler diagnostics can find this, you can have bugs in your code that compiler diagnostics cannot find that only a deeper analysis can find, like memory leaks, buffer overruns, and logic errors, those sorts of things. So let's look at an example of that. So this specific example compiles just fine with no diagnostic errors. Actually, there's one, but there's actually 2 other bugs here that a diagnostic cannot find that needs to be found with the static analyzer. So how would you, so you can find deeper bugs here through program analysis techniques. This one is simple, but imagine a very large project, thousands of files, millions of lines of code. This is where you need some sort of tool to help you. So let's talk a little bit about program analysis versus testing. So you can imagine a program as a state space that analysis explores and looking for bugs in some way. So ad hoc testing usually tests a subset of this pass in the program and only ones that that the programmer can imagine or thinks of to try. So you might usually think of these as happy paths. So usually these paths will work or can work. And it's usually just the ones that the programmer thinks of. So it's you might also think of it as testing in a very sterile, bench-like environment. So, but what you really want to do is test all the code paths, all possible transitions through your state space, looking for bugs and issues that could occur while the program occurs. So as I said, this may miss errors. So in this specific example, we missed one of these nodes because we're only testing through nodes 1, 2, 3, and 4. And that's, you might call that a happy path. It's fast, but real coverage can be very sparse, as you might see in this particular state space example. Same is true for other testing methods such as sanitizers. Sanitizers are pretty good at catching things that, such as memory access errors, things like this. But sanitizers are only as good as your test cases. All used together, a very useful combination. So how does program analysis help? So program analysis can exhaustively explore all the execution paths in all the states in your program state space. So in this specific example, you can see all the nodes in our state space are green. They've been explored. If there's an error in the code, it reports the errors as traces, or what can also be referred to as a chain of reasoning from the origin back to the beginning of the program execution. Some downsides include this doesn't scale well in all cases. You might see some path explosion. And there are some mitigation techniques that are applied. So there's bounded model checking, breadth first search approach, and there's also depth first search for symbolic execution, which limits this problem in path explosion. This can cause you to miss some errors, but there's a benefit overall to being able to explore more states in your program state space. So how does a static analyzer work kind of at an at a top level? So the Clang static analyzer, or CSA, performs a context-sensitive interprocedural and also intra-procedural analysis. It's designed to be fast to detect common mistakes, but the speed does come at the expense of some precision, and we'll discuss that in a few slides. So normally, static analysis works in the boundary of a single translation unit, intra-procedural and interprocedural. But with some additional steps in configuration, static analysis can use multiple translation units. And we'll talk about this. So let's go through a few examples. So Clang static analyzer works by symbolically executing a code. So it finds bugs without actually running the code. So in this case, it simulates the execution paths. And so we go back to our original example here. There's actually 2 divide by zeros and a garbage return error here. So we start off at the very top. In this specific case, the compiler will warn that we're dividing by a literal 0 for case 1. But moving on to static analysis, the static analyzer does a path-sensitive analysis, and it uses CFGs to create exploited graphs of the simulated control flow. So it will travel the default path. It will find, in this specific case, that A is being returned as a garbage value. And then it will explore case 1. It will see that A is equal to B divided by 0, which is a divide by 0 error, and returns that as a divide by 0 issue to be looked at. And in case 4, specifically when B takes on the value of 4, C is evaluated to 0, which then means that A is computed as B divided by 0, which ends up being another divide by 0 issue to be looked at by the programmer. So how to use a static analyzer? Let's look at a specific example. So we're going to look at the divide by 0 example. So if we run Clang analyzer on this example, we'll see that the Clang static analyzer finds an issue. which is what we want. So in this specific case, we see that case 1 signals an error. There's a divide by 0 there. For case number 4 at line 7, we see that A is equal B divided by C, which ends up being evaluated to it ends up being a divide by 0 issue. And then A can be returned as a garbage value. So we can see that the static analyzer finds the issues that, at least in this case, we hope it would find. So the other thing we can do is we can look at these issues. We can dump HTML reports and actually have a look at these. This becomes more important as the issues become more and more complex. So let's take a look at that. So in this specific case, we produced 3 different reports. We can go look at each one of these. So we can see that this specific example detects the case of case 4, where the value 0 is assigned to C, and then that's used in a division operation. So that is an issue. So let's see how we can So let's look at the next example. So example number 1, this is intra-procedural example. In this specific case, it's an array index out of bounds error. So we can see that A is attempted to be accessed out of bounds in this particular case. And this is what this looks like in the HTML report. So this is what I was referring to as the chain of reasoning. You can see that at this lowest case, this is where the error is signaled. The left operand of equal equal is a garbage value due to array index out of bounds. And then you can click back to the second item, taking the true branch, and then we can see that we can click back to the first line, which says assuming x is equal to 5. So let's look at the next example. So in this specific case, this is intra-procedural. I is declared without an initial value, and star p, it ends up being undefined or a garbage value. So this program returns a garbage value, and the analyzer is able to find this. So let's look at the next example. This particular analysis spans functions. It's said to be inter-procedural, and this ends up being a memory leak in a particular code path. So the analyzer will tell you specifically what code path this memory leak was found in. We can see that starting from 1, memory is allocated at node 2 here. We're assuming that the pointer is non-null. At line 3, we take the true branch and then we call process. But in this particular case, condition ends up being false, so we don't free the memory. So in this case, we actually leak this memory. And I think we're going to see a real example of this in one of the open source projects that we look at, except it's a little bit different than this, but you'll see what I mean. So what about analyzing calls to external functions? These examples were a single translation unit only. In other words, in the same single source file, These are interprocedural or inside of a single translation unit. What if a function calls another function outside of its translation unit? In other words, in another source file. This is referred to as cross-translation unit analysis. So an example. So let's look at main. This is a function main which calls 3 divided by the value returned from foo. In this case, foo is not known to be 0 without CTU. But let's just say somebody decides to write foo and return 0. So this is a real divide by 0 issue. So in that case, we'd want the analyzer to find this and report this problem. So CTU gives the analyzer a view across translation units that we don't otherwise have. We avoid false positive caused by the lack of information, and we help the analyzer constrain variables during the analysis. So how does CTU work? In CTU, we start with a compile commands.json file, which can be produced in a few different ways, and the source code. So in pass 1, we produce a CTU build, what's called a CTU portion of the build, and that produces call graphs, function index, and AST dumps. And then the analyzer runs and will import AST as needed for functions that are called outside of the functions that are currently in the scope of analysis. And in this particular case, the analysis is done and we'll get analysis results. So I'll show you an example. So in this case, we're going to run through a manual example, and then I'm going to show you how this is done in an automated way. So this is what a compile commands JSON file looks like. You can see that there's a directory, which refers to a particular directory that the source is in. There's a command which describes how the source is compiled. And there is the file name. And there is as many entries here as there are files in the project. So mappings that I referred to in the first phase implicitly use the compile commands.json file. So there must be a compile commands.json file present in order for this to work properly. The analysis phase uses compile commands.json to locate the source files. So we'll go through the steps here that we'll take for a manual CTU example. So the first step is to generate the AST. That's done by using an option called emit AST. And the next step is we generate the CTU index file. It holds the external definition mappings. In this particular manual case, we have to fix up the external mappings file in order to use relative paths rather than absolute paths. This is something that can be taken care of behind the scenes by automation. And then we do the analysis. We can see that we specify an analysis. We set up the analyzer to use CTU by telling it to turn on CTU analysis and where the CTU directory is, and that we want to output files in a pless multi-file format. So let's look at an example of how to process the CTU flow manually. This will help us to understand how other tools do this. So I have an example constructed from the slides that I presented to you earlier. So we'll look at some of these files. So there's main.cpp. It's just a main function that calls 3 divided by foo. Foo is a function that just returns 0. CTU.shell is just a shell script that constructs the steps manually that I presented in the slide earlier. And then there's a compile commands.json file that describes the directory, command, and files for the 2 files as part of this project. So the first thing I'd like to show you, though, is how to run the static analyzer on just main.cpp and show that the analyzer does not find the divide by 0 issue here. So it does not, which is what we expect. So the next thing I'd like to show you is, I'm not sure that I've showed you how to use scan build at this point, so I'll introduce that. So you run scan build, Clang ++ main.cpp, foo.cpp. So scan build runs, and it finds no bugs, which is interesting because there is a divide by zero there. So what this means is scan build is not comprehending the fact that main is calling foo and that foo is returning 0. So let's just see if we run the CTU script the way that we've manually constructed it to see if it finds this divide by 0 issue. And yes, it does. So let's go back to our slides. So as I discussed, scan build within Clang can be used to drive static analysis on projects. Scan build is not actively maintained for cross-translation unit analysis for larger scale projects. Ericsson's open source CodeChecker tool can support CTU flows. So I'll show you how that works. So the first step is to generate the compile commands JSON file, and you do that by using CodeChecker log -b clang ++ main.cpp foo.cpp, and I'm going to name this compile.json so it does not conflict with the existing compile commands JSON file. So it created that. So the compile command JSON file. So let's do an analysis step. So the analysis is complete. Now let's parse the results. So it did not find any issues. Now let's add CTU processing. Let's tell CodeChecker to include functions that are called from other translation units. And I'll change the directory here. I forgot a dash. Okay, so let's parse this. And we can see that CodeChecker did detect this as an issue, which is what we expected. So CodeChecker automates this process. So it does this for you. So we went through the steps of creating a compile command JSON. So we first tried without CTU. We could see that it did not see the result. And then we added CTU and we could see that it could then detect the divide by 0 issue in the code. And we tried with scan build. We could see that scan build was not able to detect this issue. So what are the benefits of CTU? So there's Gabor Horvath did a very good presentation on this a few years ago. There's a 2.4x average increase in issues found. There's a 2.1 median median increase in issues found with a 5x peak. And this is across at least 5 different open source projects: curl, FFmpeg, memcached, and tmux and vim. There were some loss defects when using CPU, so it's recommended that you use if you're going to use CTU, that you also do your analysis without CTU. So now we'll cover a Clang static analyzer modeling weakness. It does have a few, so there's one in particular that we'll cover that we can overcome. CSA does a good job modeling program execution, but does have a few weaknesses. So CSA is built for speed and common cases. The constraint solver does give up on some complex expressions when they appear with symbolic values. So an example is this example of an unhandled bitwise operation. So in this particular case, the analyzer warns on dereference of a null pointer. We'll never reach this state because by definition of this state of the code at line 3. This program is safe, albeit it's pretty brittle. So this is the warning that appears when we try to analyze it. we see dereference of null pointer loaded from variable z, core null dereference, one warning generated. So if we apply the Z3 refutation check, we will not see this issue. And another way to do this is by using, by replacing the Clang static analyzer constraint manager with the Z3 constraint manager. That's slower, so the Z3 refutation manager is preferred. There's a good presentation that Mikhail Gadela did about this a few years ago, so I recommend you go watch that if you want more details about the technical details. So we're going to cover a technical example. I'll go through some pretty specific cases for this example now, which you might find interesting. So the first case is we'll just try an analysis just using Clang Analyzer. And you can see that this is the result that we got earlier. And then what we can do is we can apply the cross check, and we should not see this issue. And then the next thing that we'll do is we'll apply the constraint, analyzer constraints, and we don't see the issue again. So we can do the same thing with scan build. And in this case, by default, scan build does not apply the Z3 option. But what we can do is we can enable the Z3 option. And we can see that Z3 does not find that issue when we enable cross-check with Z3. So then the next thing we can do is we can try to use CodeChecker. We have to parse our outputs. And we can see in this case that there were no defects found. This is because CodeChecker applies the Z3 cross-check by default without us having to explicitly enable it. So we can do the negative. We can explicitly disable it and try this again. And see that we should see the issue. And indeed we do. So you can see that there's multiple ways to run the Clang static analyzer from just Clang, from scan build, and from CodeChecker. And CodeChecker enables Z3 by default. So let's go back to our presentation. So CSA sometimes detects false positives because of the limitations in the constraint manager. And as I said, speed comes at the expense of precision. Symbolic analysis does not handle some arithmetic and bitwise operations, and Z3 can compensate for some of those shortcomings. Z3 is enabled by CodeChecker by default. If it's found, you can explicitly control it one way or the other. I've included a reference here to the Z3 theorem prover, and has some instructions in the tutorial about how Clang can be compiled to use Z3. So why not just replace the Clang static analyzer solver? Well, the first SMT backend solver was implemented in late 2017. It aimed to replace the CSA constraint solver. It turned out it was about 20 times slower than the built-in solver. So that was kind of proving the point that Performance is performance is good for the current static analyzer, and it's sufficient to handle most of the cases. That's arguable, depending on what your goals are, speed and/or precision. But you do have an option now with Z3. So a refutation approach gives us the best of both worlds. You have the Clang static analyzer speed for common cases and a chance for a Z3 solver to refute bugs that are found. So this is the approach for now. So let's put this all together. So how do we use everything we've learned so far to find some real bugs and some real source projects? So what I've done, all the examples I've done so far, is I built an LLVM Clang compiler from tip of tree, and I compiled with Z3 tip of tree. This is everything I've been using so far. And I've used tip of tree CodeChecker and scan build that comes with LLVM tip of tree. So one thing we're going to do is look at the Bitcoin curve library and see what kind of bugs are in that project. I chose that one because it's small enough to demonstrate, and it actually did have some bugs that the static analyzer can find. If you look at some projects that have been around for a while, they're pretty well debugged at this point, and you do find some false positives, but there really aren't really a lot of significant bugs and things like, say, gzip, although we will take a look at that just for grins. So I'll demonstrate how to run static analyzer on this code, just something in the wild that you pulled off of open source project. And the differences in analysis between Z3 and cross-translation unit analysis. And this is for your reference, so you can use it for your own projects. And like I said, I'm also going to demonstrate this on a well-developed project, gzip, just for contrast. So let's have a look. So the first thing is we'll look at the Bitcoin curve library. So the first thing I'll do is I'll clean this. And then I'll just use scan build. And this is going to take just a few minutes for this to build. So this compile is done, and you can see that there were some issues found. They do lack some potentially real issues. So what I'm going to do is compile again with scan build using the -V option so that we can look at some of the issues in the HTML viewer. So let's get this started again. We have to clean first, and then we'll start the compile with the -V option. I'm going to temporarily pause and then I'll resume. Thanks. So I'm resuming the -V option. Scan view will automatically open up the HTML view of the report. So let's just have a quick look at what this report looks like. So there's 43 total bugs that were found. 3 API issues argued with non-null attribute pass null. 6 dead assignments. 14 assigned values garbage or undefined. There's 1 division by 0, so forth, so on. 1 bad free, 2 use of 0 allocated. So one thing that I had spotted when I looked at this was the bad free option, so the bad free issue. So let's go see if we can find that and take a look at it. I think this is it. So So in this particular case, where the code is trying to free Scratch, and it says the address of local variable local Scratch is not memory that was allocated by malloc. So let's scroll back through the chain of reasoning and see if we can see the issue. I'm just pointing on these back arrows, seeing where this is being called from. So you can see that Scratch is set to the address of local Scratch. Local Scratch is a local variable. It's defined here. So what ends up happening is this code tries to free this. So that ends up that it appears to be a valid issue. So this found a real issue. There's at least one of these, and there's probably a few more other issues that are real that need to be looked at. So let's move on to the next examples. So the next thing I'd like to show you is how to run CodeChecker on this project. So the first thing that we need to do is create a compile commands.json. And then the next thing we'll do is we'll run CodeChecker analyze with the default options, which includes Z3 enabled and no CTU. So the analysis starts, and I will resume when this is finished because this will take a little bit of time. So the analysis is complete. So let's see what sorts of issues we found. So we found 45 issues, it appears. So let's open up this HTML output and have a look at this. So you can get some idea what kind of issues you're faced with by looking at the table of issues that were found during this analysis. This is useful just for a quick check, but it's a lot. Of course, the HTML viewer is going to be easier to manage. So let's see if we can open this up and have a look. Oh, it's a bit too big. Okay, so I'm going to go straight for that bad free again. Yep, so you can see argument to free is the address of the local variable local scratch, which is not memory allocated by malloc. So it's detecting the same issue. So let's go back through these again. So argument to free is the address of the local variable, assuming the condition's false. Again, you can see this is where scratch is being set to local scratch. So it looks like this could be an issue that somebody who's familiar with this code needs to look at. So let's just look at the list, and then we'll move on with the other examples. So you can see there's some core issues here. Some of these may be false positives, but they need to be looked at. Okay, so that was 3, 4, 5, 35 issues found. Okay, so now let's run with CTU and see what sorts of issues we find and compare that to non-CTU. Okay, that step's finished. So we analyzed the Bitcoin curve project using CTU. So let's see what sorts of results we see from that analysis. So we see 37 issues. So there's 2 new issues. Let's see if we can, we'll just have a look here. These issues look the same. I'm not going to go through the trouble of trying to figure out precisely what's different. I'll leave that as an exercise for somebody who's interested in fixing some of these issues, or at least reporting them. So let's move on to gzip. So far you have an example of how to run the static analyzer on the Bitcoin curve project using scan build and with CodeChecker. The reason why I chose this is because it's a relatively small example, and because it probably doesn't have as much development time and testing as something like, say, gzip does. So let's go take a look at gzip and see what sorts of comparative issues that we find in gzip. So first of all, I'll do a clean, and then I'll run scan build on gzip. And I'm going to use a -V option by default, just in case we find any options that it will pop up the HTML viewer so that we can see the issues in a browser. And this appears to be a lot faster than the Bitcoin curve project analysis phase. Okay, we finished with the analysis using ScanBill, and we found no issues here. So that's good. You might expect that for something like gzip. So let's run CodeChecker log and capture compile commands JSON file, and then we'll run CodeChecker. We'll run Clang analysis through CodeChecker and see if there's any differences or issues, new or different, that we see. So first we'll create our JSON file. Then we'll run our analysis. So our analysis is finished. So let's see what sorts of issues we parse. So we do see a few issues. Let's go take a look. So some of these could be false positives. So anyway, this is something for somebody who knows this code to go look at, but this is just a result, a comparative result. So I'm going to run, so we found, looks like 14 issues. So the next thing I'm going to do is run analysis with CTU enabled to see if we see any differences in results. So this analysis is finished. So let's see how many issues we find this time. This is with cross-translation unit analysis enabled. In this case, we find the same numbers. So there appears to be no difference in the number of issues that we find. So that's my demonstration. So so I encourage you to try the same thing. I'm going to leave the instructions in with the tutorial. So let's go back to the presentation. So results and conclusions. So we found some real bugs that appears in the bit count in the Bitcoin curve library. We demonstrated how more bugs can be found or refuted using CTU and Z3, and shown you how to make use of Clang tools to find real bugs in your projects and open source projects. Reconstruct the steps that I've demonstrated for you here today. So thank you very much, and if there's any questions, we can take those now. Thank you.
Hello, everybody. Thanks for coming to the tutorial. That was really interesting. I'd like to introduce Vince Bridgers, and I'm going to be reading him the questions. The first one is, do the Clang static analyzers have false negatives, or are all the bugs found?
Yes, there are false negatives, and there are ways for dealing with that. So the best way to deal with that in a large scale testing process is to use multiple ways of testing your code, and this is just one way, as I think as was mentioned in the tutorial. Thank you.
Is this talk going to be available later?
Yes, it will. There's going to be some preparation time, but it will be available publicly later. Yes.
And is it going to be on the Hoover platform for a while too?
Yes, it'll be there for some time. I believe I heard about 6 months. So you can post questions and look at the questions and the answers that are on the Hoover site. But then this will be moved over to the I think on a YouTube site.
Okay. Do we have any data showing the reduction of false positives on open source project by using the Z3?
Yes, there was a paper published by, let's see if I get his name right. Sorry if I butcher the name. Mikhail Gadela. There's a paper that was published on this that shows some specific data about the number of false positives that were reduced. I'll paste in a reference to this after the session.
Okay. Can you auto-generate test cases with the Clang static analyzer?
Not that I'm aware of. Somebody else may have a different answer for you, but I think one thing that the questioner may have been asking, you can take a large test case and reduce it, and there are ways to reduce a test case if that's what the questioner was asking, but I don't believe there's a way to produce test cases.
Okay. Are there annotations that can be inserted in the code to avoid false positives?
There's no solid way to do that today. There are ways to do that. If you look, I'll post another reference for that. There is a website that shows examples of how to suppress false positives produced by the analyzer.
The local scratch and free report seems a bit confusing, not pointing to the scratch assignment. Is that considered a bug in the checker?
So sometimes the checker can produce reports that may not be easy to follow. So what you do have to do is look at those carefully sometimes. But if you do see something that's confusing, I would encourage you to report that as an issue.
Do you have any thoughts about designing the verifiers for the CSA itself, since they can also report false positives?
Region store needs some work. That's a big one, I think, but I think that's pretty well known.
Do you have ideas on new checkers that may be useful to a wider audience?
I do have some ideas. I'm not really prepared to go into a lot of detail about that today. The biggest thing that comes to mind is working on the false positives and improving those, and also improving the reports. Those are the two biggest things that come to mind as an answer to that question. But otherwise, I will post some answers to that question when those thoughts are better formed.
Do you use the static analyzer yourself in your own software development?
Yes, I do, every day.
Was there a specific time in your career as a software developer that you decided that would be a good idea? And can you talk about that a little?
That's a great question. I could go on for hours about that. I'll keep it brief, though. So I've worked in environments where I've had to debug crashes post-mortem. And so what that's taught me is that using a tool like the static analyzer can help you find problems before they actually occur in the field or at the customer site. And that can help you save time. Sometimes it can take you hours or days or weeks to find the root cause of a problem in software from a customer report, because sometimes you're not always given the instructions for how to reproduce the problem. So one thing that the static analyzer can do for you is can help you, at least point you in the areas in the code that are suspect that you need to take a closer look at. And this is particularly true for C and C++ code. So I think that was the short answer. That's a short version.
Well, we're at the end of the questions that have been posted. So if you have any other anecdotes or anything like that that might be interesting to the audience.
Yeah, so one thing I'm not sure I covered in the tutorial is using the static analyzer on a day-to-day basis or on a per commit basis in a continuous integration flow. What that helps you do is find problems as they're introduced on a per commit basis. And that's a lot easier. So that makes it a lot easier to find issues when they occur, instead of running static analysis on your code, say every 6 months or once a year. So the other thing that does is it allows you to identify false positives and help feed ideas for improvement back into the static analyzer, so you can find problems sooner or find problems with more detail and more certainty than you currently can. So all of these things are helpful to insert this into your internal software development processes.
Mm-hmm. Well, thanks a lot for your time, and thanks for making this tutorial.
Yep, thank you.
I think we're about done for the day then. You guys can go and get your coffee break early.
Thanks for attending the talk.